All right, welcome back. Now we're going to talk about Poisson probability distribution. So it's another probability distributions, and Poisson is probability distributions for measuring things that you have a certain number of occurrences over a specified interval of time or space. A specified interval of time or space, like how many people come into the restaurant over every 10 minutes. Right? Or how many people come into the emergency room every hour? Or how many potholes are there in the road every mile? So a number of occurrences over a specified interval of time or space. And we're going to start out learning about Poisson probability distributions by downloading this slide. We're going to download it, and then we'll take it down as a PNG. And so this is slide number 39. We'll see if it gives us a number. We'll go here to downloads, and we'll look. And we've got slide, nope, we just have like, this is the second one with the 0, 1. And then we're going to go to ChatGPT, and we'll come up here because I like this prompt that I did right here. And I'll Control C that prompt and put it back in here. And then I'm going to come back over here and grab Poisson probability distributions, but I'll just grab Poisson. And I'll say, can you please explain the information on the slide attached? Going in, and I'll attach that slide so I don't forget. Upload from my computer. And explain the basics of Poisson probability distributions and why probability distributions are important statistics. And then also please give me a sample problem to work on my own. After I complete the sample problem, I will share my answers with you. I don't know what kind of sample problem it asks us to do, but we'll see what that comes up with. So we'll let this run for a second, and when it's done running, we'll go through it. I'll pause this video while it runs. All right, ChatGPT's done. Plus, I read through the slides here and did some highlighting. So we'll take a look at those in a second. Let's see what ChatGPT had to say. Basics of Poisson probability distributions. I kind of like the word. It makes me think of like an 80s band, Poison band. So there's this band Poison, which is like a big hair rock band. I don't know what songs they did. They still have an official website. That's amazing. We'll look at songs and see what songs they did. Oh, Every Rose Has Its Thorn. That's an amazing song. I think Ride Like the Wind. That's also amazing. So definitely go listen to those songs. Every Rose Has Its Thorn. I think the Guns N' Roses version's way better. They made it famous, I think. Basics of Poisson probability distributions. Poisson distribution is a probability distribution that is often used to model the number of events or occurrences within a fixed interval of time or space. These events must occur independently, and the probability of an event occurring in a given length of time or space is constant. Key characteristics of Poisson distribution. Discrete random variable. The Poisson distribution deals with discrete events, meaning the outcomes are whole numbers. So you're having a certain number of patients or customers come into the hospital or the restaurant. You're not going to get fractions of a patient or fractions of a customer. Or you have like a certain number of potholes. And you're either going to say it's a pothole or it's not a pothole. You're not going to say this is half a pothole. You're just measuring things in a discrete way. Infinite sequence of values. So any number of people can come into the hospital, or any number of people can come into the restaurant, or any number of potholes could be in the road. So the random variable can take on an infinite number of values, starting from 0 and moving upwards without limit. Hold on. Specified interval. The distribution is particularly useful for counting the number of events that occur within a specified interval, such as the number of phone calls received by a call center in an hour, the number of accidents at a particular intersection in a year, or the number of misprints on a page of a book. That's cool. Lambda. The mean number of occurrences in the specified interval is denoted by lambda. This is both the expected value mean and the variance of the Poisson distribution. So one of the properties of a Poisson distribution is that the mean and the variance are equal. And again, this was created by people who got their doctorates in statistics. And so why is the mean equal to the variance for Poisson distribution? That's a subject that's left for more advanced courses. Importance of probability distributions in statistics. Probability distributions like the Poisson distribution help statisticians and research. I just like reading about this to remind myself and you. help statisticians and researchers model real-world phenomena and make predictions about the likelihood of future events. What's the probability? What's the distribution of the probability? They are essential in understanding how data is spread or dispersed and in making informed decisions based on probabilistic outcomes. Explanation of the slide. The slide highlights the core aspects of the Poisson distribution. Usefulness is often used to estimate the number of occurrences of an event within a specific interval of time or space. Discrete. Poisson distribution deals with the random. We already know those things. Sample problem. Let's put this understanding in practice with a sample problem. A customer service center receives an average of 5 phone calls per hour. Assume the number of calls received follows a Poisson distribution. What is the probability that the center receives exactly 3 calls in an hour? It's interesting, they didn't give us any formulas here, but then they gave us a problem. So we'll jump over to our PowerPoint slides and go through these where we'll get some formulas or get a formula, and then we're going to do that problem for ChatGPT. So here is a definition. You can pause the video and read that, stuff we already went through. And then here are some examples of Poisson probability distributions, things that could be modeled with a Poisson probability distribution. So we're looking at events or occurrences over a specified interval of time or space. So number of knot holes in 14 linear feet of pine board. Number of vehicles arriving at a toll booth in 1 hour. We're looking at events or occurrences at a specified interval of time or space. Vehicles arriving at a toll booth in 1 hour is an event or an occurrence occurring over an interval of time. Number of leaks in 100 miles of pipeline. The leaks are an event or an occurrence happening over a specified interval of space, right? Number of leaks in 100 miles of pipeline. And then a little note down here, Bell Labs used Poisson to model the arrival of phone calls. That's such a weird use of arrival, you know? Why don't you just say model the number of phone calls received, or that's weird. All right, so that's, to me, like statisticians aren't necessarily the best at using English to describe things. Poisson probability distribution, which might be actually interesting just to think about, because there's this great book. We're going to take a little tangent here. And if you think about math occurs on the left side, but so does language. I don't know. The left side of the brain is where linear, logic, literal, and language all occur on the left lobe of your brain, and then emotions occur on the right. So anyhow, Poisson. Properties of Poisson experiment. The probability of an occurrence is the same for any 2 intervals of equal length. Somebody's at our house. So these are properties. The probability of an occurrence is the same for any 2 intervals. The occurrence or non-occurrence in any interval is independent of the occurrence or non-occurrence in any other interval. So you have independence, and you have, the same probability that something will occur. And then here's the math. Probability function for Poisson. So x is the number of occurrences in an interval. What's the probability that we'll have this many occurrences? We have a probability distribution. So for a different number of occurrences, we have different probabilities that, that number of occurrences will occur over a certain interval, right? So this is what the probability function tells us. Like, we could say, hey, what's the probability of 10 occurrences or 5 occurrences or 50? And it'll calculate that probability for us. And that probability is distributed for each of those possible variables, random variables. The variable could randomly be any one of these values. For any one of those discrete values, we could calculate the probability of that value occurring over a certain interval of time or space. So x is the number of occurrences in an interval. The probability of x occurrences in an interval is the function. It gives you that probability. Mu is the mean number of occurrences in an interval that's given to you. And then E is like a magic number in mathematics. It's kind of like in baking. You have baking soda or baking powder, which to me are kind of magic when you cook with them. It's like, I don't know why I'm adding this, but somehow it makes the bread or the cake turn out better. So E is like that in mathematics. It's just something you add because it's part of the recipe. And here's the recipe. So you just add a little pinch of E here, and it helps this function all work well. You've got to take a lot on faith. And you just have to take it, because that's the way people who know a lot more about stuff have told you, this is how you cook this cake. All right, I'm going to cook that cake. I'm not going to try to reinvent that. I just follow the recipe. Same thing here. So then you have E, which is this magic number. And if we wanted to, we could go to ChatGPT and we could have it explain E to us. That might be kind of interesting at the end of this. Maybe we'll do that. So there's the formula. And now having this formula, right, we could go use it. So we have u to the x. I'm just going to look here, see if there's any other mathematics that we need to know about. So there's an example. I guess we'll see the example, then we'll go do our own calculations. So since there's no stated upper limit for the number of occurrences, the probability function is applicable for values from 0 on up without limit. In practical application, boom, x will eventually become large enough so that fx is approximately 0, and the probability of any larger values of x becomes negligible. Here's an example. Arrivals at emergency room. The average number of patients arriving at the emergency room at a large hospital in a 15-minute period of time on weekday mornings is 10. So here's the average. Boom, boom, is 10. That's our mu. Okay? And what is the probability of 5 arrivals? Here's our x. 5 arrivals in a 15-minute period of time on a weekday morning. So we don't have to do any kind of like, if they say 5 arrivals in a 30-minute period of time, that might be 10 arrivals. If they said 10 arrivals in a 30-minute period of time, we might have to say, well, that's 5 arrivals in a 15 or something like that. Arrivals at the emergency room, here's our mean, here's the number of arrivals. So f of 5 is 10 to the 5th. Magic number e, negative 10. 5 factorial gives you this. So now let's take this and we'll put this over here. And we'll put this over here. Whip, whip, whip. Put that over there, and we'll calculate this one. And to do the calculation, we need to do, so I'm going to go back to the spreadsheet. So I'm going to open the spreadsheet again, and that's binomial probability distribution. So I'll create a new one here, and we'll call this Poisson probability distribution. And then here we're going to have our mean, and then we're going to have our x, which is our random variable, and our mean on this one is 5, average of 5 calls per hour, and then assume the number of calls received follows Poisson distribution. What's the probability of 3 calls an hour? What's the probability of 4 or more? So we'll do each of those situations there, and we'll just kind of like right align all this, just to be symmetrical. And then our formula is going to be, and we'll bring this one over here, our formula is going to be this deal here. And so first calculation is going to be u to the x. So we'll put u to the x. And so this is going to be, do we have an equals power? Number raised to power. And so our base is going to be the u, and that's going to be equal to, that's going to be that one. And we don't need the equal sign there. It's going to be that one. I'm going to make that absolute. And so I'm going to press F4 on my keyboard to do that. So I'll click right there and press F4. And so that's always going to be referencing that cell. And then the first one here is going to be this cell right here. That's going to be raised to that power. So there's our u to the power of x. And then we're going to have e to negative u. Okay, so again, we're going to do equal pow. And here, whoops, I want equals pow. And for this one, it's going to be e. How do I calculate e? So e equal e. I'm just wondering if there's e value. So I'm just going to come up here and put the e in, e, because it gives it to us right here. And e is also given to us up here somewhere. E. There it is. But can I get in there? I can't get in that, so I'm just going to type it out. 2.71828. Boom. And I could ask ChatGPT. I could say, quick question here. Well, I could come back to this chat. I'll do a new chat. In Google Sheets, how can I, is there a way to add e to a formula or function? Let's see what they say. Yes, you can use that. Exponent 1 will return approximately 2.7. Huh. So manually entering e, you could just manually enter that. Or example, exponent 1 times 3. If you want to multiply e by another number, say 3, you could do that. Or you could just do, all right, I have no idea what e is. Please explain to me, what is e? Please explain to me what is e and where did it come from and why does it exist? Thank you. Euler's number, denoted as e, so I guess e from Euler, is one of the most important and fascinating constants in mathematics, much like pi. The value of e is approximately that, and it appears in various branches of mathematics, particularly in calculus, complex analysis, probability, and number theory. Origin and discovery of e, so here we have some calculus, mathematical definition, why does e exist, and where does e exist and why does e exist? Naturally arises from the mathematics of growth, change, and limits. E is a fun. All right, that's all I need to know. Even though I took like 3 classes of calculus, I'm like, that didn't stick with me back when I took it, and I'm not interested in having it stick with me now. Come on, bring that one up. There we go. So here we are back at this one. And we could also do here equals exponent. And we could, oh yeah, there's Euler's number. And then we could just do 1. And there it is. All right, so E, it's going to be equal to this. Oh, we need pow, equal pow. And it's going to be e to the negative mean. Is that right? Is that what we do? Let's check our thing over here. So we want e to the negative mu. So here we have e, which is C2, to the negative mean, which is 5, and that's our mu. So we're going to put that there. Whoops, I'm on the wrong one. Oh, yeah, there, calculated. And then we need x factorial. And so x factorial is going to be equal to factorial, so factorial of a number, and we want to do factorial of that. And then we have that. And then I'm going to do this. I'm going to do a second calculation here. And the second calculation is going to be, the first one is u to the x. That's going to be equal to the mu, oh, we need pow. We need pow, and mu, comma, to the x. There, oh, but we're doing this one. It's the second one. And the next one's going to be e. It's going to be e, so we need pow. And then e to the negative mu. Boop. And then the next one's going to be x factorial. It's going to be equal to fact. And factorial is 4. There we go. And then we have that. And now we got to do the math on that. So the solution is going to be parentheses, this one times this one, right? And then it's going to be divided by that one, the factorial. And then we're going to copy this over and put it here. And I'm going to make these percentages. So the probability of, for our problem that we were given here, the probability of 3 calls in an hour is 14.04%, and the probability of 4 calls an hour is 17.55%. That's pretty interesting, right? Like you could have a random variable, some variable that randomly you choose, and you can figure out what's the probability of that occurring, and there's a distribution, probability distribution of, depending upon what value the variable is, it could randomly be any of these values. We have a probability of what that value is going to, what's the probability of that value randomly occurring. Use the Poisson probability formula to calculate these probabilities. After you've worked through the problem, share your answers, and I'll check them for you. So I'm going to just copy these, Control C, and put that here. And I'm going to put here 14.04%. And here I'm going to put 17.55%. And you know what? I think we did everything right, but I maybe, don't know if this is correct. And so we'll see what, there's always a little uncertainty. All right, let's see what ChatGPT has to say about it. And recap, let's check your calculations. I didn't say get the good work up here, so maybe I didn't get that correct. The average number of calls per hour, that one there, lambda, we using Poisson distribution to calculate the probabilities. Here's the formula. And so they use lambda here, which is the average number of calls. We were using the mean, and the book was talking about it as mean. And there's the mean, and then, so that's kind of cool. See the different notation. And so we get this, and then we get that, and we get 1404. So correct, we did it right. That's awesome. And then calculate the probability, find the probability of receiving 4 or more calls. You can either calculate the probability for 0, 1, 2, and 3 calls and subtract their sum from 1. Since the total, that makes sense. Or use a Poisson table or software to directly compute this. So we'd have to calculate the probability. What was probability receiving 4 or more calls? So we calculate for 0, 1, 2, or 3, and then subtract that. Let's do that before we see here. So we're going to do 0, 1, 2, and 3. And to do that, I'm going to put in 0, 1, 2. I'm going to put in 3 rows, insert 3 rows above. And we're going to put in 0 and 1 and 2 and then 3 and 4. All right, so and then that's our mean. So here is this one is for 3, this one is for 4, and we need to do it'd be cool if these were in order. So but I guess I'll do it down here. I'll do 1, 1, 2, 3, and oh, we need 0. 0, 1, and I'll make these big. 1, oh, dang it, 0, 1, 2, and 3, and then we'll subtract that from 1 because the total probability of anything is 1. It's 100%. So for 0, and I'm just trying to figure out how can I structure this to replicate things. So we're going to have, I like this function, this amount right here. So I'm going to insert 1 column to the left, and I'm just going to copy this here, Control C, and put that there. And I'm going to put probability here, and then u to the x is going to be equal to the mean, lambda. I'm going to make that absolute. Oops. I'm going to make that absolute. Oh, come on. I'm going to make that absolute F4 and put the dollar signs around it. I'm going to zoom this in. Well, I guess I got to get out of that. So I'm going to zoom this in just to make this bigger so we can see it better. That's better. So this is going to be equal to that. And it's going to be that times our formula, u to the x. So we need pow. So I'm going to come over here and do pow. So do pow equals pow. And it's going to be that. And it's going to be u to the x. And our x is going to be this. And I think we kind of want our x's going left to right, but that's right. So just trying to figure if there's some way to do that. I'll do my x's over here. So x's will be 0, 1, 2, 3. Because now as we move them left to right, and I'll just make these a little bit, boop, 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 a little bit smaller. There we go. And so I'll do my x over here, and it'll be that one. That's my 0. So now as I move that over, as I copy this over, it's going to continue to reference that, but it'll move from 0 to 1 to 2 to 3 because that's relative. So as I do this, oops, come back. As I do this, right, and if we look at the formulas on that, it went from B5 constant to F2, G2, H2, I2, F2, G2, H2, I2. All right, so there's that. And then we have e to the negative u, so we're going to do equals pow, and it's going to be e, and we're going to hold that constant, and that's going to be to the negative u, and that one is going to be held constant too, right? Because we have e to the negative lambda, or mean, because lambda is equal to variance in Poisson. So just put that in, and then we can format that number, and we'll just format that as like a number like that. So there we go, e to the negative u. And we need more decimal places on that. So we're going to go to format, we're going to go to number, and we're going to go to custom number format, and we're just going to add I don't know, 5 decimal places. There we go. Wow, it's all 0.064. Well, that makes sense, right? Because it's all e to the negative u. And e is this, and negative u, negative lambda. Here it's mu, but ChatGPT was using lambda. That's going to be the same one. And then x factorial, and so our x is going to be equal to fact, and it's going to be this one, right? So that, and then we'll copy that over, Control C, and we'll get different amounts there. And then the probability is going to be equal to this one times this one divided by this one. If I can find my mouse, there we go. And now we'll format this one. Let's make this one percentage. Cool. And then we'll copy this over. And then we'll say equal to 4 or more is going to be equal to 1 minus, and we'll put in here this plus this plus this plus this plus this. And I need to get rid of that D18. There we go. So B19, C19, D19, E19, B, C, D, E. And then in my parentheses, and did I get my end parentheses in there? No, I put it in the wrong place. It needs to be over here. There we go. All right, so the probability is 73.5%. And if we come back over here, 73.5% is the right one. So cool, I learned something. I just didn't read through that question correctly because I was looking for the probability of 4 or more. And I just calculated here the probability of 4, but we need 4 or more. So we do some other kind of function or formula, or we could do it this way. That's the Poisson distribution.